Natural hazards, catastrophic geological hazards. Types of geological hazards. Floods causes heavy rainfall, river overflow, dam failure, and rapid snowmelt. Impacts, loss of life, property damage, soil erosion, and water contamination. Landslides causes heavy rain, earthquakes, volcanic activity, and human activities like deforestation and construction. Impacts, destruction of infrastructure, loss of life, and disruption of transportation networks. Ion earthquakes. These natural phenomena are primarily caused by tectonic plate movements, volcanic activity, and human activities like mining and reservoir-induced seismicity. The impacts of earthquakes can be devastating, leading to building collapse, infrastructure damage, tsunamis, and ground rupture. Volcanism. This occurs due to magma movement beneath the Earth's crust and at tectonic plate boundaries. The effects of volcanism can be quite severe, including lava flows, ashfall, pyroclastic flows, disruptions to air travel, and even climate effects. Avalanche. These dangerous events are triggered by heavy snowfall, rapid temperature changes, and human activities. The impacts of avalanches are often catastrophic, resulting in the burial and death of individuals, destruction of buildings and infrastructure, and major disruptions to transportation. Tsunami. These powerful waves are often caused by underwater earthquakes, volcanic eruptions, and landslides. The impacts can be devastating, including coastal flooding, destruction of property, loss of life, and contamination of freshwater sources. Cloudbursts. These sudden and intense downpours are usually caused by localized rainfall in a short duration, often associated with thunderstorms. The consequences can be severe, leading to flash floods, landslides, and significant property and crop damage. Prediction of hazards. Understanding and forecasting these geological events is crucial for mitigating their impacts and ensuring the safety of communities. Floods. Predicting these devastating events involves several advanced methods. Weather forecasting plays a crucial role, as does river gauge monitoring. Additionally, satellite imagery provides a broader perspective. Technology such as Doppler radar and automated weather stations are indispensable tools in this process. Landslides. To predict these occurrences, experts rely on monitoring rainfall and soil moisture levels. Ground deformation is also closely observed. The technology used includes GPS sensors, remote sensing, and ground-penetrating radar, which all help in providing early warnings. Earthquakes. Predicting these natural hazards involves seismic monitoring and analyzing historical data. Early warning systems are also essential. The technology here includes seismographs, accelerometers, and GPS for detecting ground movement. Volcanism. Predicting volcanic eruptions is crucial for mitigating risks. We use several methods: monitoring gas emissions, observing ground deformation, and tracking seismic activity. Advanced technology plays a significant role in this, including volcanic observatories, satellite monitoring, and thermal imaging. Avalanche. Predicting avalanches involves analyzing snowpack, forecasting weather conditions, and studying historical data. Technology aids in this process with snow stability tests, remote sensing, and the use of avalanche beacons. Tsunami. Predicting tsunamis is vital for coastal safety. We rely on methods such as monitoring seismic activity and using ocean buoys to detect wave changes. The technology behind this includes tsunami warning systems, satellite monitoring, and dart buoys for deep ocean assessment and reporting. Cloudbursts. Prediction methods include weather radar and atmospheric moisture analysis. Technology such as Doppler radar, satellite imagery, and automated weather stations play a crucial role. Mitigation of impacts. Floods. Structural measures involve building dams, levees, and floodwalls. Non-structural measures include floodplain zoning, early warning systems, and public education. Landslides. To mitigate the effects of landslides, we can implement various structural measures like retaining walls, slope stabilization, and drainage control. And non-structural measures are just as important. These include land use planning, reforestation, and the development of monitoring and early warning systems. Earthquakes. Mitigating earthquake damage involves a combination of structural and non-structural measures. Structural measures, such as constructing seismic-resistant buildings and retrofitting older structures, are crucial. Non-structural measures like conducting earthquake drills, public education, and implementing early warning systems also play a vital role. Volcanism. When it comes to mitigating the hazards of volcanic activity, structural measures like lava diversion barriers and strengthening infrastructure are essential. Equally important are non-structural measures such as evacuation planning, hazard zoning, and raising public awareness. Avalanches, well, they can be incredibly destructive. To mitigate their impact, we use a combination of structural and non-structural measures. Structural measures include avalanche barriers and controlled explosions to trigger smaller, less dangerous avalanches. On the other hand, non-structural measures involve avalanche forecasting, public education, and zoning regulations for buildings to ensure they are constructed in safer areas. Tsunamis, those massive waves, require robust mitigation strategies. Structural measures like seawalls and tsunami-resistant buildings play a crucial role in protecting coastal areas. Additionally, non-structural measures such as early warning systems, well-planned evacuation routes and drills, and comprehensive public education are essential to ensure communities can respond swiftly and effectively when a tsunami threat arises. Cloudbursts, those sudden, intense rainfalls, can cause severe flooding. To mitigate their effects, we rely on both structural and non-structural measures. Structural measures include improved drainage systems and check dams to manage water flow. Meanwhile, non-structural measures encompass early warning systems, afforestation efforts to stabilize the soil, and careful land use planning to minimize flood risks. In conclusion, effective prediction and mitigation of geological hazards require a combination of advanced technology, sound engineering practices, and comprehensive public education and preparedness programs. By integrating these strategies, we can significantly reduce the devastating impacts of these natural disasters on communities and infrastructure.